It first comes off, sit and command the spacecraft. Those folks actually talk in real time to the Deep Space Network and controllers there as well. In the back of the room, we have the systems engineers, the mission operations manager, as well as specialists in autonomy and guidance and control. And this room is actually quite a bit larger than you see. There's a whole wing that goes off to the side where we have specialists in propulsion, communications, thermal engineering, who are all watching the same data and eagerly waiting to see the spacecraft complete its burn and come back and tell us how well it did.
Hard to see what the best seats in the house are. Yeah, I guess.
Well, they've given all of them the best seat in the house. They each have all the data that comes off the spacecraft at their fingertips all the time.
So, we talked about configuring and commanding and a lot of those terms that we've heard Ken in some of his updates. Take us a little bit through what he means. When he says configuring and commanding, what is he talking about?
Configuring and commanding. The spacecraft has switches, lots of switches for units that are either turned on or off, lots of software commands where you tell the spacecraft to put this sort of data into a packet that's going to come down to the Earth. Hundreds and hundreds of different states that the spacecraft can be put in. It's a very complicated computer. And it's not just one computer. There's actually a main computer that does most of the work of operations, and there are two computers that are watching that computer all the time to see if it's making any mistakes, and then it will take over and say, no, you need to fix this or you need to fix that. And so building and testing this very complicated system was very challenging. And right now there's a command list that's been put on the spacecraft that is literally thousands of lines long. And the operations team has to go through that list and make sure every single command is right. It's in the right place, it's in the right time, it's got the right arguments, it's going to do the right thing. And they've tested this and simulated it. It's very complicated.
And then tweak.
All right.
Okay, so this is what you're talking about here, right? You're at the base of you're at the end of the firing.
End of the firing.
But it's not completely over. There's still some adjustments to make sure that happens.
Changes that the propulsion system makes in order to shut everything down and get the total momentum of the. They don't want to have the spacecraft spinning it all when it stops. They want to very carefully control that and stop on a dime, so to speak, and have the spacecraft very still when the burn completes.
So if we looked at the simulation of the burn itself now, it would look a little bit different, I would think, than when we saw the first rotor, would it? I mean, it's just the amount of thrust that's coming in.
They're all happy there. All right. Perfect.
Yeah, right. So here,
what's up, propulsion engineer?
you're seeing right. They're shaking hands. They're celebrating. They're happy.
Yeah.
So it looks that's the best indication that the burn have gone well, and that they got that data back that the burn was completed.
Yes.
I can see the simulation there too.
Yep.
I'm walking around and I'm watching people walk around that room, and I'm seeing certain people I know what their jobs are, and they're not all shaking hands yet. They're not all. So there's still some looks in their faces like they still have some things they're going to check out.
It's going to be a long night. They got a lot of data to look at, but so far it's been a great night.
So that was that first indication there that the burn was completed. It completed like it was supposed to.
Yes.
But I'm betting that no one yet is willing to make the call officially that is in orbit. This picture is telling a lot, but to temper expectations is very hard to do in this case to see how excited some people are in that case.
No,
and probably I would think the next thing we'd want to do is if we're ready to go back to mission operations for an update.
not yet.
Okay.
No, I'm pretty sure I saw Ken in the operations center.
So he's going to have to run back out.
Yeah, we need to give him a minute to catch his breath.
I will give him. He's got to remember his responsibilities here before he does that. So at this point there, if we saw that Doppler plot, which managed to hang on through the burn that we were watching,
That's right.
We were wondering
to confirm the state, but we'll let everybody know as we progress to that point.
The mission operations manager is getting everybody to sit back down and look at their screens, I think.
Yeah, right,
so.
All right, so now we can go to mission operations. Ken outside the mock. And Ken, we saw something that looked pretty encouraging over here. Fill us in on what happened.
Yeah, Mike, we're pretty excited. Preliminary results look like the burn went just as expected. It's still early, but everything looks perfect at this point. We are going to wait until we receive high-rate telemetry from the spacecraft, at which point we can officially confirm that we've captured into orbit, but so far it's looking just great.
Okay, can you kind of explain the difference of what the kind of data we were getting before? We talked about it here a little bit, but we're getting different rates of data. You're talking about getting much higher quality data that's going to happen next. What are we waiting for to happen next?
So now that we believe the burn is completed, the spacecraft will reorient itself so that it can point our high-gain antenna back onto the Earth. And once that's done, both the onboard RF system needs to reconfigure and the ground system needs to reconfigure, but then we'll start getting high-rate telemetry data, and we'll be able to verify individual parameters, subsystem by subsystem, on the ground from the spacecraft, and then confirm exactly the state of the spacecraft, where it is, how the burn performs, and so forth. So once the engineers have a chance to receive that data and then look through the results, we'll be able to make an official determination.
Okay, so I guess was it hard to drag you out of there and then get them back to their screens?
I'm happy to share the good news. We're all pretty excited so far.
Kevin, we'll back to you in a bit. What we'll look at now, Mike, let's go back through that simulation.
Okay.
Okay, because as we were describing what was happening here, and there was a burn here and a thrust that was moving around. Let's go back to that orbit, the thruster simulation again, and see what's happening. Let's take us through what we were, where we were in this process. Now, this is what we're seeing in real time.
So real time here, you can see that the animation shows no more thruster plume. The spacecraft has got to change its attitude now so that the high gain antenna will point at the Earth, and that's another change of state in the spacecraft. It's got to check and make sure that its solar arrays are at the proper angle, and you see how far the solar arrays are turned so that they're almost pointed at the sun. Rather than having the face of the panel, the blue panel there, pointed towards the sun, it's almost like it's edge onto the sun. That's because the sun is so intense that they feather the arrays way, way back in order to keep them cool enough to keep operating. And that's still more than enough power to run the whole spacecraft. And that's just a factor of how intense the sun is so close in Mercury orbit.
Environment. Let's go back to this first simulation here. Now we'll see it in context, right? Before we were just saying what was going to happen, we've seen the reports and heard what's going on here. So what we've already seen happen is the spacecraft go over the planet, that close approach, come back out, firing the thrusters, and take us back here to where we might be in this process now. We're getting there. And then take us back through, here we go, what we're watching for now, where we are now in this process.
And so the spacecraft makes small adjustments to make sure that it continues to follow that command sequence. Set the solar angles to this attitude, turn the spacecraft to such and such an attitude, continue to track the Earth in the high gain antenna beam as it goes around the planet. And that will cause the spacecraft to roll around the sun line. So if you imagine a line leaving that sunshade straight towards the sun, the spacecraft effectively will turn around that line in order to keep tracking the Earth the whole time. This is a very smart spacecraft. It knows where it is in space, it knows where the sun is, it knows where Mercury is, and it knows where the Earth is. And it will continue to point different parts of the spacecraft, the shade toward the sun, the antenna towards the Earth, based on that knowledge throughout its flight. And one of the interesting things that it'll do soon is it will bring into its decision-making process the fact that it's around Mercury, and the fact that it knows where Mercury is, and it will start tracking that. And that's one of the new things that the spacecraft will do today. Whereas before, it always knew where the sun was and where the Earth was and where it was, but it didn't say, well, there's my target planet, and I'm going to keep track of my target planet too. So that's a new thing that it'll do today for the first time.
You mentioned too about the intensity of the heat by the solar panels. There's also a lot of tools and techniques. It's one thing just even to get Messenger to survive at Mercury. It was also very important to find ways to have it get there and survive on its trip there. So here's a look at some of the steps that the team took to have the spacecraft survive on its way to Mercury.
Once Messenger gets into Mercury's orbit, the science team can start collecting data about the smallest and least studied terrestrial planet in our solar system. Questions about its core, magnetic field, and density, among other things, will finally be answered. Just how does a spacecraft survive the...
Can you explain a little bit then about, where Messenger fits into NASA, exploring the solar system, and what we hope to learn from Messenger, where that fits into what we want to learn?
Well, this is, let me see, if we count Venus, Mars, Jupiter, and Saturn, we have now, tonight we will have orbited the 5th planet in the solar system. That's a major accomplishment. I was talking to the team before the burn and reminding them how important this was. I mean, you only go into orbit for the first time around Mercury once in human history. And that's what was accomplished tonight. So that in itself is just a major, major accomplishment, something the guys and gals here can tell their grandchildren someday. It only happens once in human history. And it's just beginning. We're going to learn more about Mercury than we ever dreamed of. You've heard a lot of the scientists talking about what they expect to learn. I will predict that that won't be the most exciting stuff. The most exciting stuff will be the stuff we weren't expecting and the stuff that will enable us to ask new questions that weren't even thought of. And that's what we found every time we orbit a planet, whether it's Venus, Mars, Jupiter, Saturn. So our goal is to first fly by planets, then go into orbit around planets, and for instance on Mars eventually, as we did, to land on planets. And then ultimately our long-term goal is to bring samples back from planets, and we hope to do that, for instance, on Mars sometime in the not-too-distant future.
This is NASA's year of the solar system. And so if you can kind of give us a look at what's ahead for NASA. You mentioned some things that we'd hope to do. What's ahead? What's coming up in the year ahead?
This is, I think, in the 50 or 60 years of planetary exploration, this has got to be the most exciting year ever. It started a few months ago when we flew by the first comet back in November, and then we flew by Hartley just a few weeks ago. We are pretty sure we're in orbit around Mercury right now. We're going to be orbiting an asteroid for the first time, Vesta. Our Dawn mission goes into orbit around Vesta in the summer. And then some really big launches. We're going to be launching about $4 billion worth of observatories this summer. The first one is going to be GRAIL around the moon to understand better what the moon, how the moon was formed, what it's really made out of, from the core all the way to the outer surface. Then we're launching a month later in September, Juno, the first solar-powered satellite that's going to go all the way out to Jupiter and orbit it to learn more about its magnetic field, its so-called magnetosphere. And then the big mission is going to be the day after Thanksgiving. Finally, we're going to launch the Mars Science Lab, which is going to be a rover the size of a compact car, nuclear-powered, so it doesn't have to rest at night. It can work 24/7. It can go 60 kilometers, perhaps even 100 kilometers over its mission. It's just going to be a super mission. It's going to carry instruments that look for organic molecules to understand if the conditions on Mars were right at some point in time for the formation of life. I can't say. It's going to be an exciting mission.
It sounds like an exciting year for what's going to be happening around the solar system, getting information. So, Dr. Waller, thank you, and I guess we're all going to look forward to what's going to happen over the next year.
Thank you.
We've also talked a lot about, we were talking about the instruments actually, and it kind of seems like center stage, the star almost of the payload, because it seems to be the thing that everyone will notice is the camera, the pictures. So Louise Proctor, you're the deputy project scientist for Messenger, but someone who has worked intimately with the cameras, responsible for a lot of the imaging. And I guess, I also, your eyes are some of the first that see the pictures that come down from Mercury and that have since we've been in orbit. We got a lot coming up over this next year, but kind of tell me a little bit some of your favorites of what you've seen so far.
Certainly. Well, obviously it's a very exciting time. It's been very exciting for the last few years. I wanted to show you a few of my favorite images. I'm very self-indulgent. But one of the first ones you've seen a couple of times tonight, and this is a view of Mercury as we first saw it with Messenger. And the key here is this huge bullseye feature to the top of the image, which is the Caloris Basin. It's large enough that the state of Texas would fit inside it. And this is a significant image for many reasons, one of which is that it proved to us that the camera was working just fine. We got these fantastic images, and the spacecraft was also where it was supposed to be. But also, I think for a lot of us, it brought it home that we really were there. We really were flying by Mercury. You build the spacecraft, you launch it, you wave it goodbye, and then you don't touch it or see it. You communicate remotely with it. And so when you see the images, it really shows you that, yes, you really are there. It's all worked. It's become real.
So there's the first part, yes, we saw it, but there's been some surprises, too.
There have been quite a lot of surprises.
What were some of those?
Well, the next image I pulled is of a feature that was found right in the middle of the Caloris Basin. This is affectionately referred to as the spider for obvious reasons. It's now, it has an official name of Pantheon fossae. And what we're looking at here is some huge cracks in the surface of Mercury, and they radiate outwards, and they go almost to the edge of the Caloris Basin. So some of these cracks you're looking at here are about 5 miles wide, and they travel for hundreds of miles to the edge of the basin. And we've never seen anything like this before in the solar system, certainly not inside a large impact basin. And we still don't fully understand how this formed. It may have something to do with the fact that Caloris slowly rose up for the millennia after it formed, but this is something that we're still looking into, and it certainly was. And so here we know that the large basin formed first, and then was flooded with this volcanic material, and then a smaller crater on top. So we're unraveling time by looking at these images.
So to see those, over the next year, looking at some of the plans of what you expect to see.
Very exciting. I mean, even before we start our official science orbit, where the day we turn the camera on, the very first image we're going to see is of the South Pole region that we haven't seen before. So very first commissioning image is going to see brand new terrain. So very exciting. Also, we'll be able to target some areas of interest at resolutions almost 10 times higher than we were able to see them from the flybys. So as many people have said tonight, there are going to be many more discoveries to come.
Well, I appreciate you sharing your favorites. Like I said, I know you're going to have more. If we come back to see you soon, you're going to have a lot more favorites, self-indulgent as it might be. We're going to go back to mission operations. Ken?
Thanks, Mike. We're still not ready to make an official determination. However, I can let you know that we have high-rate telemetry from the spacecraft. So we know that the burn ended nominally. We know that the spacecraft is fully in control. It is now oriented back at the Earth. We are receiving high-rate telemetry. The engineers are pouring through all the data, making sure everything is truly exactly as we expected. But all indications thus far is that it's been a perfect evening.
Yeah. I think this is also, a good time too when we were checking this. Messenger really is one of several missions and projects that are happening at the Applied Physics Laboratory, taking on difficult challenges and making them work. And over half a century in the space business, the APL has accomplished quite a few things. So let's take a look at some of those, what APL has planned and what it's done. Okay, so after that look, joining us is Andy Danzler. He is the Civilian Space Programs Manager here at the Applied Physics Laboratory. And Andy, some of the missions in that video, including Messenger, it seemed to be a little typical that there's certain challenges that APL is willing to take on and make them succeed.
We try to specialize in one-of-a-kind missions that go to extreme environments, difficult missions, things that haven't been done before. Obviously, you heard a lot about Messenger, going to Mercury, very hot, very difficult. We also have, we launched in 2006, the Stereo mission. The Stereo is actually 2 spacecraft that look at the sun from different vantage points. And in that way we're able to get literally stereo images, but also three-dimensional science. In fact, for the first time ever, we're able to see the entire solar globe by using the Stereo mission. And not just the solar disk, but actually the entire globe. So we watch solar storms form on the far side of the sun, watch as they evolve around the sun. Very difficult mission to pull off. You heard mention of Pluto. We have the New Horizons mission. The New Horizons was also launched in 2006. Another very difficult mission. It's got to go a great distance. It's got to go far away from the sun where you can't use solar panels, so it uses what's called RTG. In fact, it's a very long trip, so even though it was launched in 2006, it doesn't get there until July of 2015. But coincidentally, today it actually passes the orbit of Uranus, planet Uranus. So still got a lot to go. Of course, it's very cold. That won't be an orbit. That'll be a flyby. And hopefully past Pluto, then it'll encounter what we call the Kuiper Belt objects, objects even past the orbit of Pluto. And again, in terms of difficult environments, we're building the radiation belt storm probes. Those are, again, 2 spacecraft. We're building those right now for launch in about 15 months. And where they go is they stay in Earth orbit, but they orbit in and out of the Van Allen radiation belts, natural radiation belts of Earth. Most spacecraft try to avoid these radiation belts.
Okay, I'm going to interrupt just for a second. We have a chance to go back to the mock, and Ken is outside. Ken?
I'm here with Eric Finnegan. He's the mission system engineer for Messenger. And I guess I want to start with Eric. Are we ready to make an official determination on achieving orbit?
Absolutely. The Messenger spacecraft went into orbit around Mercury tonight. We can confirm that through the Doppler signals that we have seen. It is extremely exciting in the mock. Everybody was hooping and hollering. We were elated. We are in orbit. Now there's a lot of work left to be done, but we are there.
That was good, yep. We still have Eric, congratulations. I mean, it's part of you're the mission systems engineer, the spacecraft, putting that together, a lot of work that went into having this done. So I'm guessing at that moment I can see it in your smile, number one, there's a bit of relief that this part is over, but it also looks like there's more work to do.
Oh, absolutely. There's more work to be done, but I want to congratulate this entire Messenger team, the guys in the mock, the engineers. They've worked really, really, really hard over the last number of months to prepare the command sequence, to simulate the command sequence, to run it over and over again, to sit in rehearsals. I think they've seen this burn 10 times before tonight, and they were happy to see it go really nominally right down the alley. We hit the trajectory to within a half a sigma for those my engineering friends in the crowd. It was right on the money.
All right. Eric, we were talking a lot this evening about the different ways the team is going to know that it's in orbit, and then we've seen a few moments this evening where there was applause and then lighter applause and heavier applause and standing and handshaking. Tell us, the moment, what came together? What pieces did you put together to get to this point to say, yes, Messenger is in orbit around Mercury?
Well, the first indication of things were going to go really well, we started the burn. We were all worried that we were going to not be able to maintain communications with the spacecraft through the burn. When the main engine lit off and we kept a lock on all of the ground stations, I knew things were going to go really well, but certainly weren't in orbit yet. The burn had to go at least 70-75% of the way there to make sure we were in orbit. So once we passed that mark, there was a lot of relief. We're at least in orbit. We may not be in the perfect orbit, but we're there around the planet. We may need a cleanup maneuver, but we kept burning. There's another mark. I think folks might have thought it was kind of interesting, but there is a piece of protection we turned on during the burn just before the end to make sure that if things were going not really well, it would turn off. We passed by that mark without a problem, and then I knew things were really going to be well. As soon as the burns turned off, we did lose signal with the ground stations a little bit. It was actually a good thing because that means the acceleration of the spacecraft stopped at the exact time, and at that point, when we picked back up the signal and we're traveling along the nominal Doppler line, we knew we were in orbit. Then it was just a matter of how well we were in orbit. And that came a few minutes later when we did enough estimates of what the Doppler residuals were to make a preliminary estimate that we were about a half a sigma from our nominal trajectory. And that was very, very relaxing.
Say half a sigma. Can you say about how far that is from the real thing? Say how close these things come.
As close as this is as close as you possibly get to being perfect. There were some numbers we were quoting in the mock. I don't want to quote them here because I want to see the final data when we get it. But they were lots of decimal point and lots of zeros before they got to a 1, saying whether we were good on acceleration or good on pointing.
Take us through a few steps of what does happen next.
So right now, so we turned back to downlink attitude. We downlinked telemetry in the spacecraft. The next big mark was, was there something on the spacecraft that happened that we held off to make sure the burn went, so to protect the spacecraft. We looked at all the telemetry that came down from the spacecraft, and there was not a single thing that fired. The spacecraft was nominal. The next step is to turn the star trackers back on to maintain an attitude lock. That came and went without a problem. Then we need to reestablish all of the protection we turned off to make sure this burn would happen. We did that. Right now, the spacecraft is nominally pointed to the Earth, downlinking normal telemetry, reconfigured like nothing ever happened, although now it's in orbit around the first planet to the Sun.
All right, well, Mr. Finnegan, congratulations and happy St. Patrick's Day.
Thank you very much.
Thanks, Mike. And with that official determination, I think we're done with the updates from the mock, and we're going to go and continue to attend to business.
All right, Ken, thanks for all your work tonight. Great job. Thanks.
Thank you.
We were just talking about the missions that were happening here, some of the extreme environments, the tough test. This is one that passed. Some of your feeling about what a mission like this means to an institution like APL? Just personally, what you think this means for the team here?
Well, you look at how many missions have accomplished. It's like Dr. Weiler was saying, how many missions are in orbit around planets ever throughout the history of the aerospace industry. And to be one of those institutions that has put a spacecraft in orbit around any planet, but particularly this one, it's just an amazing feeling. It's a great day, not only for APL and NASA, but the multiple institutions across the country that have helped to put this mission together.
Yeah, there was contribution, I think, from states if we put them on a map. They're in different places here, and I think what it illustrates and talks a little bit about what it means to put those different pieces of a team together. We're talking about missions that it completed 10 years ago with NEAR. That was innovative, landing on an asteroid, orbiting and landing on an asteroid. We're now putting spacecraft in orbit around Mercury. We're going to fly past Pluto. The amount of expertise that comes in a team like this and pulling that all together in a short amount of time seems to be a challenge in itself, but something that seems to be working.
Yeah, we're doing a fine job here at APL. We have, again, this stereo mission already in space. We're building the radiation belt storm probes, again, launch in 2012. Looking forward to other missions as well. But yeah, it seems to be the formula we've got is working pretty well.
Okay. Andy, thank you, and congratulations.
Thank you.
It's going to be a good night here. Again, to remind you that we are still providing updates on the web, and if you haven't seen the Twitter page yet, you need to get there and see what updates are still there. And there's full mission coverage on nasa.gov, the Messenger site, as well as the Messenger mission page out of the Applied Physics Laboratory. Michael, let's see, from the team member point of view, when something like this happens, you were there when it was built, tested, launched.
Yeah,
this is what it was about.
This is really exciting. And one of the things that Eric said particularly caught my attention. He mentioned the fact that the spacecraft is now in orbit, but that none of the fault protection has tripped. There's nothing that went on in the spacecraft during the burn to indicate that any problems happen whatsoever on any subsystems. And there are hundreds of what we call rules running all the time. And these rules check temperatures and power levels and states of different parts of the software. And they look at the physical and the electrical state of the spacecraft continuously. And through this very critical maneuver, none of those tripped. None of those things said, oh, this is wrong or this is in trouble. It wasn't just right down the middle when it comes to the orbit insertion, but all the operations were just right on target. And that's a very sensitive system that doesn't hesitate to take action when something goes wrong on the spacecraft. So.
And, going through the testing and from the beginning, you said getting tripped up and watch that thing happen. To watch this, and to be here to see this go into orbit and watch it happen, to see it work the way that it was planned and designed, be incredibly fulfilling for a member of the spacecraft.
This is fantastic. I can't wait myself to get over the Mach and shake some hands. This is really great. No, go ahead.
We'll go in fact, we're going to go back over to the simulation again to see where things were. This is, I guess after watching the burn and moving things along, to see it without the engine firing, almost looking like it's in orbit around Mercury. This is the current image that we're looking at here of what we would see if we were looking at the spacecraft right now. And we had said early in the program that the view you were looking at, this simulation would show what the spacecraft would be if it operated exactly the way it was supposed to. And that's what we're looking at right here. Okay.
Good evening, Michael.
So as we're going through these final paces here, I know we saw the moon and mission operations. We talked to someone who I thought was pretty happy, and that was Eric Finnegan, the mission systems engineer. Now we're looking at mission operations live with our update. I think you see a different sense of activity in mission operations now. Ken is taking a well-deserved break. Yeah, there is. I'm surprised they're still there. But that's what we have in mission operations and seeing here, and you can see the events that had happened through the evening. And what we're looking at now, again, we had said how just thrilled, enjoyed Eric Finnegan was, but I think we could find some people who would be equally, if not more happy. I talked about shaking hands. They probably already shook their share of hands and had a lot at stake here when the mission first formed and went through its different flybys. To get to Mercury, I am here with Peter Bedini, who is the project manager for Messenger, and Sean Solomon, principal investigator for Messenger. First, congratulations to both of you. You look relieved. You look exhausted. You look a combination of things.
How about happy?
And there is happy. That's the smiles that were out there. And it's the first time I think I've seen you smile over the last couple of weeks. So tell us a little bit what this feels.
I'm always smiling inside.
Just your reactions from both of you. This has been a tense moment. To get to this point, it wasn't easy. Tell us about what it's like now that you're in orbit around Mercury.
Well, I for one was never worried. It's interesting being there and understanding that some people have worked on this for 15 years, and from design to early proposal, design, development, couple thousand people at least worked on this, and over that long a time, it's quite a delayed gratification, but a wonderful